Hello everyone and welcome to your 23rd lecture in historical geology. We're getting close to the end now. We only have 25 lectures to go, so after this one you're only going to have 1 week of lectures left. Okay, so 2 more lectures. After this we got to finish Cenozoic life, and then we're going to finish up with a brief lecture on human evolution. So how and where our bodies evolved, and kind of the animal side of humans. How did we come to be? So we'll answer some of those questions in the final lecture. This lecture, though, we're going to present some information to you about the geology of the Cenozoic. Okay, so you can see things have changed dramatically from what you saw in the Mesozoic, right? You start to see woolly mammoth and saber-toothed cats, lions, caribou, things that look a lot more familiar to us. You also see a lot of snow on the ground because we went through periods of times you'll see when a lot of the Earth's surface was covered with ice. Okay, those are during the ice ages, during the Pleistocene, and we might not go back now to a glacial period. We'll talk about that a little bit more later. But anyway, that's what we'll be doing today. Dug a little bit about geology in the Cenozoic. So now we've gone through so much. We've talked about the Hadean, the Archean, the Proterozoic eons. We've talked about the Paleozoic and Mesozoic eras of the Phanerozoic eon. And now we're going to finish up the last era of the Phanerozoic eon. And what's that? It's called the Cenozoic. So we are doing the Cenozoic today. Okay. So the Cenozoic consists of 3 periods. We call it the Paleogene, the Neogene, and the Quaternary. Okay, the Quaternary basically means recent stuff. Okay, because the Quaternary only started, just maybe like 2 million years ago, so not very long ago. The Neogene and the Paleogene are the vast majority of the time here. So this isn't actually split up spatially in an equal way at all. Quaternary is very short compared to the Neogene and Paleogene. Okay, so we also, for the first time in the Cenozoic, you need to know epochs. Okay, so the Paleogene consists of 3 epochs. That's the Paleocene, the Eocene, and the Oligocene. The Neogene consists of the Miocene and the Pliocene. And the Quaternary consists of the Pleistocene, which was basically the Ice Age, and today, which is the Holocene. We call this the Holocene. Okay, so welcome to the Holocene, welcome to the Quaternary, welcome to the Cenozoic. You're here right now in the Phanerozoic eon, in the Cenozoic era, in the Quaternary period, in the Holocene epoch. Okay, so you do have to know those epochs: Holocene, Pleistocene, Pliocene, Miocene, Oligocene, Eocene, Paleocene. Okay. Here are the dates. So the Pleistocene, you can see that's the start of the Quaternary. It was only less than I thought. I thought it was about 2 million years, 1.6 million years. The Paleocene, of course, is the first one. That starts 65 million years ago. Eocene, 56 million years ago. Oligocene, 35 million years ago. Miocene, 23, and Pliocene, 5 million years ago. Okay, and you can see the Holocene only started 0.01 million years, which is just about 100. What would be 0.1 million years would be 100,000 years ago. 0.01 million years ago would be 10,000 years ago. So Holocene only started about 10,000 years ago. 0.01 million years ago. Okay, so the Mesozoic ends 65 million years ago with a bang. Of course, that was the famous asteroid that wiped out the non-avian dinosaurs. A meteor impact near the Yucatan Peninsula is probably where it landed. It was probably about 8 miles across, this impactor, and it threw up a lot of dust into the atmosphere. It created tsunamis, global fires, and it also just dramatically disturbed the climate and disturbed food chains, which ultimately brought about the demise of the dinosaurs. Now, we think that the impactor landed here somewhere off the coast of the Yucatan Peninsula here, because we've actually picked up, done gravitational measurements. Now, of course, this is under the ocean right now, so we can't really see what's going on. However, we can use gravity. And what we're actually doing is we're picking up, we have an instrument that can record very, very, very subtle changes in gravity. Okay? So we can remotely sense these structures that are maybe buried deep beneath many layers of sediment. So this is covered with water, it's covered with sand, but I think you can start to see these concentric outlines that look like a crater right here off the Yucatan Peninsula. And it's about the right size and the right age for what we're looking for. So we think that this is probably the spot, the epicenter of the impact crater. Now, why do we think that an impact of a meteor ended the dinosaurs? So this is why. 1981, you had a father and son team, Walter and Luis Alvarez, they discovered a very interesting thing between the Cretaceous. Now, I know it's kind of weird, but because a lot of these terms are German, they spelled Cretaceous differently, so they spelled it with a K. So this K represents Cretaceous, this T represents Tertiary. These are different terms that are kind of older, archaic terms. I shouldn't say archaic, but decades old. We don't use those terms anymore. But Cretaceous, Tertiary, represents the barrier between the boundary between the Mesozoic and the Cenozoic right here. Now, right between these layers, there's a very interesting layer here. Okay, so right on the boundary. So the son, Luis, has his hand right on the boundary layer right there. Okay, so we're going to talk a little bit about this. So this was discovered again by the father Walter Alvarez in 1970s, and they noticed that fossilized plankton shells suddenly disappeared, and that there was a worldwide clay layer everywhere. I mean, everywhere where you find the KT boundary, you find this ashy clay layer. And you suddenly see the end of fossil planktons, but other things. I mean, you see the end of dinosaurs, you see the end of a lot of different species that were around in the Cretaceous layers, but not in the Tertiary layers, okay? So you see a mass extinction occur between these two layers. This particular place they're looking at is Gubbio, Italy, 1981. But you find a lot of interesting things in this clay layer that exists globally, all over the world. And it separates the Cretaceous and the Tertiary, okay? You find high concentrations of an element called iridium, okay? Iridium is got the, it's IR, that's the elemental symbol. And iridium is a very interesting metal. It's extremely rare on Earth's surface. However, it's abundant in meteorites, very abundant in meteorites. So we find in all this clay between the this little thin layer of clay between the Cretaceous and Tertiary, we find a lot of iridium. We find shocked quartz. That means high pressure quartz that can only form under extreme pressures. Okay, like the kind of pressures that would predominate during an impact of a meteorite. We find glass spheres, little glass spheres, and they're just little like maybe millimeter sized little glass sphericals. Those little glass sphericals represent basically liquid droplets of rock that were melted, ejected into the atmosphere, and cooled, and would have fallen almost like a shower of, you can imagine it would have been such a thing, because you would have been showering little over the whole surface of the earth. You would have been showering down, not rain, but little droplets of melted rock, because the impact was so tremendous. It sent all of this liquid rock, threw all this liquid rock into the air, and it cooled and fell as little droplets of glass. It's an amazing thing to think about, but it's true. Also, we see a lot of wood ash, as in global fires. Okay, so very interesting things that all kind of point to the same source, which was a large meteorite impact. Okay, so there's a close-up of that very, very, very special, important clay layer in between the Cretaceous and the Tertiary boundaries. Okay, so this is a measure of iridium. By the way, it's always funny because I know who listens to the lectures and who just looks at the slides, because on the lecture assignments, so often if people aren't listening to the lectures, they'll mistake this IR for iron, and I get a lot of people putting iron. IR doesn't stand for iron, it stands for iridium. Okay, so iron is Fe. Anyway, we see a very high level of iridium in this layer between the Tertiary and the Cretaceous. And notice this scale down here. This is not a linear scale. It's what's called a logarithmic scale. So this is 10 to the 1, 10 to the 2, 10 to the 3. So this isn't, we're not talking about, just 3 times as high here. We're talking about 1,000 times. So we find concentrations of iridium that are 1,000 times greater than the rest of the world, okay, the rest of Earth's surface. So it's very suspicious, and again, it points to a large meteorite impact. So anyway, that's what ended the Cretaceous, ended the Mesozoic, and started us off into the first period, or sorry, I shouldn't say the first period. Well, I guess I could say first period, the Paleogene, the first epoch of the Paleogene, the Paleocene. That's what started us off into that first epoch, the Paleocene. Okay, so let's go into some of the major tectonic events. Now, looking at a global map during the Eocene, now, of course, this is still 50 million years ago, you can see that things kind of look, pretty close to actually how they look today, right? This looks familiar to you now, right? We see North America basically oriented how we're used to. You see South America, Africa. You see India has not yet collided with Eurasia, but what's happening now is the closing of the Tethys Ocean. So the Tethys is closing up here, and what's going on is that Africa, Arabia, India are all going to be forcing themselves up against Eurasia. Okay, so this is Eurasia right here, and we're going to get mountain building occurring along this boundary right here. Okay, and that mountain building gives us a lot of the big mountains that are around today. It gives us the Himalayan mountains, and it gives us the Alps and the Atlas Mountains all through here. Okay, so notice another thing I'm going to point out is that Arabia, the Arabian Peninsula, has not yet broken off from Africa. So notice they're still connected here, and India has not yet begun to collide here. So let's talk a little bit about Cenozoic orogenic belts. Okay, so mountain belts that have been developed during the Cenozoic. This stunning picture is of the Himalayan mountains, which are the tallest mountains in the world right now. Of course, they're not the tallest mountains to ever exist, but they are probably pretty close. Okay, so they're very, very large mountain belts. The Alps in Europe are actually part of the same overall orogeny as the Himalayas. So you get mountain belts all through this area because Africa, Arabia, and India are all colliding with Eurasia, and that is caused by the closing of the Tethys Ocean. So during the Cenozoic, you see the closing of the Tethys Ocean. And what's kind of cool is that the very last little bit of the Tethys is still here. I talk about this a lot because I just think it's really cool. This is the last little bit of the Tethys. This is the Caspian Sea. And it's just a little bit of the Tethys. It's actually the oldest seafloor in the whole world. Actually, it's right here at the bottom of the Caspian Sea. But now it's kind of weird because it's no longer like an open ocean. It's now kind of like a fresh, it's actually kind of transforming and becoming less salty. So the salinity in here is about 1.6%. The salinity in the rest of the ocean is about 3.5%, 3.4%. So it's not as salty, and it's becoming fresher little by little. One day probably this will become basically an inland lake. But it's a very deep lake because it still has original ocean floor. So anyway, that Caspian Sea is just a little bit that's left of the original Tethys Sea. The Himalayan alpine belt formed with the collision of Africa with Eurasia, the closing of the Tethys, the current Caspian Sea and Black Sea in Eastern Europe are the remnants of the Tethys seafloor. 250 million year old seafloor there. It's the oldest seafloor in the world. Okay. Around this time, we also had the collision of India with Eurasia. So 55 million years ago, we began the collision. So right about at the beginning of the Eocene, basically, we start getting the collision of India with Eurasia. That has lifted up the Himalayan mountains and the Tibetan plateau. Okay, so 21 million years ago, that's what it looked like, and it's still happening today. India is continuing to slide underneath the Himalayas, building up the Himalayas, and creating the Tibetan plateau. Okay, so very it's a very highly uplifted, high elevation area. Okay. So another very important mountain belt that is currently being created right now is the Circum-Pacific Mountain Belt, aka the Ring of Fire. So right now what's happening is the Atlantic Ocean is expanding. It's been opening up for a long time now. You know that. It started in Triassic, right? We started the opening 250 million years ago, basically. We started with the opening, or 225 million years ago, started with the opening of the North Atlantic and South Atlantic. And since that time, the Pacific Ocean, which is really just the Panthalassic Ocean, right, has slowly been closing. Okay, so the Pacific gets smaller and smaller every year, and the Atlantic gets bigger and bigger every year. Okay, so we're going to see the Pacific plate shrinking as it is totally consumed at the margins at subduction zones. So you have subduction zones completely surrounding the Pacific plate, swallowing up the Pacific. Okay. So that has created, volcanic arcs all around, going from the Andes Mountains through the Sierra Madres in Central America, the Rocky Mountains here, the Cascade Mountains here, the Aleutian Mountains here, right? The all of Kamchatka and the Japanese Arc, all of the mountains you find around here. These are, of course, all not really mountains, but volcanic volcanic islands. But all those things are part of the Circum-Pacific Mountain Belt that is being created by the subduction of the Pacific Ocean, okay? Pacific seafloor. So taking a look now at the Paleogene, you see India has not yet collided with Eurasia yet. But this is the right here, the Tethys. And India is moving this way. Arabia is not detached yet, but Africa, Eurasia are going to start colliding, creating the Alpine Mountains, the Alps, and the Himalayas here. Okay. So notice in the Paleogene, sea levels are still very high. You can see a lot of Eurasia is flooded. A lot of the Amazon, India, Africa, North America are all flooded, right? So moving into the Neogene, the Mediterranean, you'll notice, is landlocked. There are very high evaporation rates there, and you get about 2 kilometers. This is here. Let me erase all the ink on here. So you can see the Mediterranean is totally landlocked. So usually we have this, Straits of Gibraltar right here that open up the Mediterranean to the larger ocean. But at this time, the Mediterranean is almost completely landlocked. And so the Mediterranean has these very high evaporation rates because it doesn't have this ability to refresh itself with the open oceans. And these are very highly evaporative areas right here at about... Actually, the Mediterranean is the saltiest, some of the saltiest ocean water in the whole world because it's right here at about 20 degrees latitude. It's right where you get the highest levels. 25 degrees latitude is where you get the highest levels of evaporation. So these areas are highly evaporative, and you actually get about 2 kilometers of salt deposits forming on the bottom of the Mediterranean. So India and Eurasia are starting to collide now in the Neogene. So you can see the collision. This is starting to build up the Himalayan mountains. Okay, into the Quaternary. Let me erase some of this stuff on here. Moving into the Quaternary. So if there's the Paleogene, the Neogene, now the final period, you can see how everything, the North Atlantic and South Atlantic are expanding, and things are getting drier and more spread out, and you can see the water levels are dropping, right? You all see how Paleogene things were covered with Epiric seas, a lot like them during the Mesozoic. Now things are starting to kind of dry out, sea levels are dropping. So anyway, in the Quaternary, you can see that the Red Sea right here has started to open up. There's the Red Sea. That means Arabia is starting to split off, and this is going to be the new ocean. I mean, someday this is going to be a major ocean, right, between Africa and the Arabian Peninsula. So this is going to continue to collide over here. This is going to continue to collide and build up the Himalayan mountains here. Okay. We also see in the Quaternary widespread glaciation. So you'll notice that there are no glaciers really, maybe just a tiny bit here during the Paleogene and Neogene. But during the Quaternary, we see widespread glaciation on Greenland. We see it on Antarctica. And during the Pleistocene, we get glaciation all the way down, covering a lot of Eurasia, a lot of North America as well. So let's kind of zoom in now and start talking about what's going on in North America at the time during the Cenozoic. So during the Paleocene, again, we're talking about hot, humid weather conditions, talking about high sea levels, and a lot of the North America's still kind of covered with ocean water at this time. Notice that there is no Hudson Bay. So normally there is a big bay right here. Okay, that's all filled in with water. That's the Hudson Bay. We don't have that formed yet because that was actually carved out glacially. And we haven't had that glaciation yet that has carved out the Hudson Bay. Okay, but you can see things were temperate. You had temperate forests here in Canada, maybe temperate forests here in North America. So right here, a lot of the plate tectonic action is still happening on the west coast. You can see the Appalachians by now are very much eroded down. Okay, so these were the big mountain ranges during the Paleozoic, but now they're just kind of pretty modest mountains in the Cenozoic. So all the action is happening here on the west coast, where you're getting the continued subduction of the Farallon Plate beneath North America, and that's lifting up the Rocky Mountains. Okay, so we call this orogeny that continues to build up the Rocky Mountains in the Cordilleran. We call that the Laramide orogeny. So climate is warm, humid, temperate forests over much of modern day Canada. Okay. So the Laramide orogeny, let's go in a little bit more detail with that. The Laramide orogeny begins in the Cretaceous, ends in the Cenozoic, and it follows directly on the heels of the Severe orogeny. So this is all part of the continued subduction of the Farallon Plate. So the Laramide orogeny is different than the Severe orogeny in a few ways. Now, this is a major tectonic event that forms the Rocky Mountains, going from 70 to 40 million years ago. And it occurred in the interior of the plate. So the uplift was very different than the Severe orogeny because it wasn't just on the margins of the west coast, but the stresses were transferred into the interior of the plate. Because you'll notice that the Rocky Mountains today are not on the west coast per se, right? They're not in California. They're in Colorado and closer to the interior of the country. So how did the subduction of the Farallon Plate create these mountains in the middle of the country? So that's how we're going to get, that's kind of what we're going to explain here in just a minute. So this occurred 1,000 miles from the coast, okay, 1,000 miles from the subduction zone, but they are subduction related mountains. The Rocky Mountains are subduction related mountains. So we're going to kind of explain what happened here. So the Severe orogeny, how did it occur? Occurred with the subduction of the Farallon Plate, right? How did the Laramide orogeny occur? It occurred with the subduction of the Farallon Plate. But the subduction angle changed, and that's what created a more interior, more easterly deformation with the Laramide orogeny versus the Severe style orogeny. So some differences, key differences between Severe style deformation versus Laramide style. Again, both originating with the subduction of the Farallon Plate, but they're different. So one thing is that, of course, Severe, it's more to the west. The deformation was occurring more to the west. With the Laramide, it's occurring more to the east. In the Severe orogeny, it's more thin-skinned. In the Laramide, it's more thick-skinned. So you can see that really the deformation here is occurring with the overlying sedimentary rocks. Do y'all see that? So you can see that the faults that are building up the mountains, they're thin-skinned. They're only affecting the sedimentary rocks that are sitting on top of the craton. In the Laramide, you can see that the faults forming these mountains are cutting right through the skin, the sedimentary rocks at the surface, and going right into the craton, uplifting the entire craton. So these are also, notice, these are generally lower angle faults than these ones are higher angle, okay? And when I say lower angle versus higher angle, I mean, like, if you look at this, okay, that's a horizontal line. If you look at that angle right there, that is a higher angle than this right here. That's more of a horizontal fault, okay? So these are higher angle faults that are cutting into the craton. So they're deep faults, thick-skinned faults, okay? So the style of faulting and folding in the mountains was very different. The Laramide mountain building was more to the east. It was in the interior of the continent. Notice the severe orogeny of the mountains are thin-skinned, consisting of low-angle thrust fold belts, and superficial sedimentary rocks are mainly the thing that are being cut and folded and faulted. That's not true during the Laramide. The Laramide, you have thick-skinned, consisting not only of the sedimentary rocks, but also the underlying Precambrian basement rocks, the cratonic rocks. Faults were nearly vertical, high-angle faults. So how did this occur? Why was there a difference in the severe style versus Laramide style orogenic events? So what we think happened that caused this difference in styles is flat subduction. So normally plates subduct at approximately 50 degrees. So, you know, if you have a flat surface here, the subduction of the seafloor is happening at maybe 50 degrees. Okay, so that angle right there between the subducting seafloor and the surface is about 50 degrees. However, we think that during this period, we got something called flat subduction. So instead of having that normal subduction angle, subduction was kind of going like this. Okay, so here's the subducting slab. Okay. And so maybe it was, 10 degrees or something like that. And that's what transferred the stress deep into the interior of the continent. Okay, so that's why you're getting, 1,000 miles transfer of stress deep into the interior of the continent that way. So it was what's called flat subduction or low angle subduction. Okay, so there you go. This is a picture of the flat subduction that is moving because the Sierra Nevadas in California were basically created by subduction of the Farallon Plate during the Cretaceous and severe orogenies. Okay, now you're getting this flat subduction that's transferring stresses into the interior, lifting up the Colorado Plateau and the Rocky Mountains. Okay, now why did flat subduction occur? Nobody really knows. One very popular hypothesis is that a mantle plume, kind of a hot, buoyant mantle plume, sort of buoyed it up or lifted up the subducting plate, kind of stopped it from sinking into the mantle. That might be true. There's evidence for that. There's evidence against it. So it's just an idea. But this is, you're going to see a lot of this plume activity happening in the Cenozoic in North America. So it's not just this. We're going to see Yellowstone and the Columbia River flood basalts also originated from plumes like this. So with nearly horizontal subduction, igneous activity ceased. So you didn't get so many igneous rocks because, usually the subducting plate melts as it gets deep into the mantle. But here you didn't get so much melting of the mantle. And we're getting more just uplift instead of volcanism. So we don't get so much igneous activity. We're getting more deformation, uplift, and folding and faulting of the rocks. Okay, so deformed mostly by vertical uplift versus the low angle severe style thrusting. Okay, so this uplifted the Colorado Plateau. So the reason that we have the Grand Canyon, right, is because the Grand Canyon is in, you have this Colorado Plateau, covers Utah, Colorado, New Mexico, Arizona. The reason that you have the Grand Canyon is because this area uplifted and it exposed all of these deep buried, very, very deeply buried sedimentary rocks. Over time, the Colorado River cut into these rocks, eroded them and exposed them at the surface, which is why you have the Colorado River flowing there at the bottom. If Colorado River did all this damage, it carved out all of these rocks. It's pretty amazing how much energy is represented here. I mean, think of how much work it takes, how much energy it takes to dig this big hole, right? So that was all done by the Colorado River. The Rocky Mountains, again, were also created by several orogenies, okay? The last one being the Laramide. So beautiful. And that's just breathtakingly beautiful. I mean, my gosh. I could just look at that all day, stare at that all day. The Rocky Mountains reflected in the pool here and the pine trees. Absolutely gorgeous. But anyway, the Rocky Mountains were created by a few orogenies, right? We have the Nevadan, the Sonoma. Well, I should start from the beginning. The Sonoma, the Nevadan, the Sevier, finally the Laramide. Okay, so there you have it. There's the Rocky Mountains going all the way from, actually extending all the way. This is part of the larger Cordilleran, going all the way from Canada, Alaska, through. That's why we have the Canadian Rockies and the American Rockies, right? And it also continues along to the Sierra Madres in Mexico. Okay, so it's all part of the same, really the same thing. And of course, I mean, ultimately they connect up even with the Andes. So, you know, this whole margin was part of this subduction of the Pacific and Farallon plates. The little remnants of the Farallon here, that's called the Juan de Fuca now. So we call this the Juan de Fuca. And that's still subducting and creating the Cascade Mountains here that we're going to talk about now. So the Paleogene was one of continuous Mesozoic igneous activity on the West Coast. So that's when you had the emplacement of the Sierra Nevada batholiths, the Idaho batholiths. And we're going to have that continuing igneous activity continuing on into the Cenozoic with the Cascades. So I'll talk about those in just a minute. I want to talk also about the Columbia River flood basalts. So these were pretty amazing. During the Miocene, we had the formation of the Columbia River flood basalts. So these were just tremendous levels of igneous activity. Again, all connected, we think, in part with the subduction of the Farallon plate, but also we're thinking connected as well with the development of a mantle plume here during the Cenozoic. So these amazing hexagonal columns that you see were not carved by anyone. These are naturally forming. So when you have very deep basalts coming out of the earth, forming like lakes of basalts, and I mean like hundreds of feet deep, okay? These are, I mean, this isn't the best picture of them. I'm going to show you a picture about how, give you an idea how deep these magma lakes were. But these were erupting at the surface, ejecting just tons and tons and tons of basalt during the Miocene. So these hexagonal columns you see here are formed naturally when deep lakes, pools of basalt cool, and as it cools, it contracts and forms these geometric patterns, thermal cracking. Okay, so it's just kind of these cooling cracks. Now, what you're seeing here, this is a picture of the Snake River in Idaho. Okay, here are the Columbia River flood basalts, and you can see just how deep these are, right? From there to there, you know, hundreds of feet deep, okay? So this outpouring of basalt was tremendous. It was 200,000 cubic kilometers of lava over a period of 3 million years. So 200,000 cubic kilometers. So just to give you an idea, that would be like 100 kilometers by 100 kilometers by 100 kilometers would be just 10,000. So maybe I should say 100 kilometers by 100 kilometers would be 10,000. So maybe we should say 100 by 100 kilometers by 1,000 kilometers, right? Would be 100,000. And think of that kind of an area, which is, I mean, you know, the size of a state, like the size of Montana or something like that. A big state, maybe not Montana, but maybe Wyoming or something. 2 kilometers deep with basalt. Tremendous amount of basalt was erupted. We don't have anything like that today. Hawaii has ejected 750,000 cubic kilometers of basalt, but it's done it over a period of 85 million years. This was done over a period of 3 million years. Okay, so a lot of basalt was ejected very fast here. Just to give you an idea for comparison, Mount St. Helens, which is the biggest eruption we've had, single eruption we've had in America in our history, it was only 1 cubic kilometer. Okay, it's amazing. So some places, like I said, the basalt is 2.5 kilometers thick, very deep. You know, that's like deeper than like the deepest lake we have. We had pools of basalt forming at this time that are deeper than the deepest lakes. Okay, so the Columbia River flood basalts, 17 to 14 million years ago. It's not certain exactly what caused them, but they are suspiciously close to Yellowstone, which, as you probably know, Yellowstone has a supervolcano underneath of it. It's erupted many times. I think there's been like 10 eruptions or more of Yellowstone. Yellowstone started erupting 16 million years ago, very close by. So it seems like, given how close the Columbia River flood basalts are and how close they are both in time and just geographically, it seems very reasonable to think that perhaps they're created by the same mantle plume. That's kind of a hot plume coming up from the mantle. Okay, so here's the Columbia River flood basalt. Again, it's about 14 million to 17 million years. We have different eruptions, 1, 2, 3, 4, 5, 6, 7 eruptions of Yellowstone over the last 16.5 million years. Okay, and you can see they're pretty close by, relatively close by. You'll notice that these eruptions keep moving to basically to the east, right, with time. So the reason that they keep moving to the east is because North America is moving this way. Okay, with the subduction going on right here, North America is moving that way. It's moving that way, and there's a stationary plume here. And as North America moves over that plume, it continues to move to the east. Okay, so that's a hot spot. And then Hawaii has the same thing. Okay, there's this Hawaiian hotspot track, and you can see this line of volcanic eruptions that gets progressively older in a straight line. So it's the same reason. Hawaii, there's a stationary plume, and the Pacific Plate is moving over it. Okay, so the fact that both massive Yellowstone hotspot eruptions occurred so close to the Columbia flood basalts seems like they are connected somehow. So this is how it works. There's a plume coming up from the mantle. It's just a heat plume. Okay, it's not actual material moving. It's just a anomalously hot area. It creates these volcanoes, but as the lithospheric plate continues to move this way, so you get a volcanic eruption there, but eventually that volcano moves off the plume and a new volcano will form. So that's how you get these subsequent eruptions that are in a line. See what I mean here? You get these volcanic eruptions of Yellowstone in a line because the plate is moving over the plume. Okay, so Yellowstone eruptions are supervolcano eruptions. We have never had a supervolcano eruption in human history. Now, there have been humans around while there have been these kinds of eruptions. However, we have never had in recorded human history where people actually were practicing writing. We don't have any accounts of what these must have been like for people. But of course, at this time when these were occurring, there have only been kind of people around for about 160,000 years. I can't remember when the last major supervolcanic eruption was, but we don't have any. Well, there's never been one of these in human history, basically. And so these are massive, though. Supervolcanoes are massive. There's nothing like it to even compare. Mount St. Helens you can't compare it. Krakatoa, which is the largest eruption that's ever occurred in recorded human history. I can't remember, it's 1884. It can't compare. Yellowstone releases maybe 1,000 cubic kilometers of material when it erupts. Mount St. Helens releases 1 cubic kilometer. So you're talking about a volcanic eruption that is 1,000 times larger than anything we've seen on Earth in human history. So these are massive eruptions. Devastating. They would be devastating. I mean, it would be if you ever had a Yellowstone eruption or a supervolcanic eruption, it would be a total game changer for human society. You know, it wouldn't make us go extinct, but it would be a major impact on the world. It would make coronavirus not seem like a little blip, right? So anyway, Yellowstone though literally sits on a caldera crater in the last super eruption. Yellowstone is 45 miles across. Okay, so you're talking about a crater 45 miles across. Okay, it's tremendous. You know, just the crater takes up a good chunk of the state of Wyoming. Okay, so anyway, moving on from that, we want to talk about the Cascade Ranges. So Cascades, beautiful mountain range there in the Pacific Northwest. It has about 1,000 different volcanoes there. And it's very much like the Andes Mountains. It's a classic subduction arc made of andesite. Okay, it's started in the Oligocene, continues today. The subducting plate is the Farallon plate, but we don't call it the Farallon anymore. We call it now the Juan de Fuca. Okay, so the Juan de Fuca is very small, and it's just the remnants of the Farallon. And you know, the Farallon's been subducting for hundreds of millions of years. Okay, so it's maybe not hundreds, but many tens of millions of years. So, or maybe 100 million years. So it's been taking a long time to die, but it's about to die now because where we have the Juan de Fuca is just very small now. So here's the beautiful Cascade Mountains, and you can see it looks a lot like the Andes Mountains. You know, and that's because they're created very much in the same way. So the Cascade Ranges, it was responsible for the last volcanic, or actually the only volcanic eruption we've had in the contiguous 48 states of America, which is Mount St. Helens in 1980. It's a major eruption. 1 cubic kilometer material. It's a major eruption. So, the Cascades also have beautiful Crater Lake. I'm not sure if it wasn't the first national park, but Crater Lake was one of the first few national parks. But Crater Lake is in Oregon. Basically just a caldera that has a caldera is just a collapsed volcanic vent. Okay, it's a crater that has collapsed, and there's a crater left from the volcanic eruption 6,000 to 8,000 years ago. And you see this little island in the middle, which is called Wizard Island, is actually the resurgence, the repopping up of that vent as it bulges forth with new magma. And someday it'll erupt again, but we don't know when. So probably no time soon. Anyway, moving along, we got to talk about basin and range. So here's beautiful Death Valley, California. Death Valley has a very ominous, terrible sounding name, but it is really a very beautiful place. And if you ever get a chance to visit Death Valley, California, I highly suggest you do, because it's just a gorgeous one in a million kind of places. I wish I could just go over show you all the pictures of Death Valley. Maybe next semester I'm going to have to show more pictures to capture some of the beauty of it. But it has these beautiful sand dunes, of course, but it also has Artist's Palette, and as well as Mosaic Canyon. Really gorgeous area. So Death Valley is part of the Basin and Range province. So it's an extensional province on the western, takes up a very large chunk of the western half of our country. So during the Miocene, as you know, you had these spreading ridges. You had the Farallon plate subducting. This is a transfer boundary, a core transform boundary. There's a lot of subduction, a lot of collision going on here. Okay, so you had all this collision. Gosh, I have all these stupid arrows going. Okay, and that creates the San Andreas fault system, right? That's the transform boundary that has the San Andreas fault system right there. So anyway, the basin and range was created by extension of the western half of our country. Okay, so when the convergent boundary turned into a transform boundary, okay, so this used to be right here in the San Andreas fault system. This used to be a convergent boundary, but the plate is done. That portion of the Farallon plate is gone. It's not there anymore. It got totally swallowed up, and now it's turned into a transform boundary. So once it turned into a transform boundary, the compression here stopped. The compression here stopped, okay? And you get basically a resurgence, a rebound of the crust, an extension of the crust. So it's kind of like if you were to imagine crinkling up a piece of paper, and you crinkle it up and then you let go and you stop compressing it, that piece of paper is going to kind of rebound and crunkle back out, okay? So kind of just to show you, imagine this. Here's Western North America, okay, here's the West, there's the East, and we're going to start, okay, so this is the original boundaries of it, right? And we're going to start crinkling it up with eastward force from subduction of the Farallon plate, okay? So we're going to start pushing this, pushing it. The compression causes folding and faulting of the crust and mountain belts. So these are like the severe orogenies, right? The laramide orogenies. So you're creating all of the Rocky Mountains and the Cordilleras as we crunkle up the western edge of North America. Okay, so we compress with all that subduction. But once that compression stops, because the Farallon plate is gone, it's been swallowed up, the west coast now becomes a transform boundary, okay? So now without that compression, things are going to start to rebound, okay? We've taken away that hand pushing, and now things are going to rebound, okay? So the crust begins to relax and rebound, and it starts to extend after many millions of years of compression. So things extend out like that, and you can see how the crust kind of you can see all these fault blocks form and they tilt, and you get this series of basins and ranges, okay? So you get a range, a mountain range, a basin. A mountain range, a basin, a mountain range, a basin, a mountain range, a basin, a mountain range. So you get this series of basins and ranges. So this again shows how this happens. The crust thins out. Okay, you see the crust thinning out, and you see these series of basins and ranges forming. You all see that? So that's how basin and range developed, okay? So as the crust thins out, you get decompressional melting beneath the thinned out crust, because if the crust thins, you're releasing some of the pressure, and that release of pressure is going to lead to decompressional melting, and just like decompressional melting like you get at mid-ocean ridges, and it's going to lead to lava pools and volcanic eruptions in the basin and range province. So basin and range also has a lot of these volcanoes forming as well. So you can see the basins. Okay, here's the basins, the basins, the basins, and I'll get another color to make the ranges, okay, the mountain ranges. So here's the mountain range, mountain range, mountain range, okay? So it's extending out, and the mountains are going to erode and fill these basins up with all sorts of sediments. So you can see, this is a beautiful picture, shows you exactly what I'm talking about. You can see all the little wrinkles here. Do you all see all these wrinkles that are going on right here? Those are all series of basins and ranges. And you'll see this if you ever fly over Nevada, you know, maybe you're flying to California or something like this, you'll get an eyeful of basin and range province as you fly over Nevada, Arizona, Colorado, parts of New Mexico. And it goes all the way up even into Wyoming, okay? So part of the basin and range also, this thinning and extension of the crust led to the formation of actually a whole continental rift zone. So right now, the Rio Grande Rift is an active continental rift. Someday, this is going to rip our country into two pieces, you know, not right now, but someday it probably will, because the Rio Grande, it's ripping across here, and it's filling up with a river. Okay, that's why the Rio Grande flows where it flows. It flows down this rift valley, and it's creating a lot of volcanism around here. So if you go through Albuquerque in this area, there's a place out here called El Malpais. You know, if you know Spanish, you know El Malpais means the bad country. This is an area totally covered with basaltic flows. So there's a lot of lava flows from the extension and decompressional melting that accompanies continental rift areas. So you could see that the Rio Grande area, this Rio Grande fault block, has dropped down a whole 10,000 feet. Okay, and it's filled up with all these sediments. So that's why, obviously the actual valley, if you go down into the Rio Grande Valley, you don't go down 10,000 feet. The reason you don't go down 10,000 feet is because that valley has filled up with sediment. Okay, so it's filled it up with kilometers of sediment. But it has dropped down a total of 10,000 feet, and it's created a low country, and that's why the Rio Grande flows where it does. But eventually, this is going to rift apart, and it's going to create a new ocean basin right here. This is a classic continental rift zone. Okay, so moving away from that into the Cenozoic formation of the Gulf Coast Plain. So just a little bit about this. This maybe looks much more familiar to you. This is, kind of a typical picture, something you might find along our Padre Island or something like that. So this should look kind of how it looks in Corpus Christi, because we're part of this whole Gulf Coast Plain. So the Gulf Coast Plain is a kind of a shelf of sediments that have been created from all the erosion of both the Rocky Mountains here and the Appalachian Mountains here, carrying these sediments down into the Gulf of Mexico. So the Gulf of Mexico has this very expansive continental shelf of sediments that have formed. And that's why, you go around here, it's very flat. It's very, the water, there's a lot of shallow bays, of course, and a lot of shallow water here. It's because you have just these expansive shelves of sediments that have been left from the erosion of the Rocky Mountains and the Appalachian Mountains. And the rivers have brought all that sediment in here into the Gulf of Mexico. As you know, the Mississippi River flows into the Gulf of Mexico. There are several major rivers here in Texas that bring sediment into the Gulf of Mexico. So during the Paleogene, the sea levels were high. Much of the Gulf Coast was inundated with water, and these were lowlands that collected sediment from both the Cordillera and Appalachian mountain belts. So, this area that we're in right now, you see, let me get the ink off the page here and go to maybe red color here. But you can see that, where we're at right now used to be underwater. So that's why when you go digging around here, we have a lot of basically fairly recent sediments that are marine sediments. They're like marine muds that were deposited, during maybe before the Pleistocene. Okay, so when sea levels were a little bit higher. But we have a lot of mud and sediments that were brought down. You have to dig really deep around here to actually get to bedrock. Okay, we got very, very thick layers of sediment here that have been brought in from the Cordilleran and Appalachian erosion, and also the fact that we were underwater for so long that deposits a lot of marine sediments. So anyway, I think that's all I want to say about how the Gulf Coast Plains form. So now we're just going to take a little ride through each of the epochs. We're almost done here, but just kind of wanted to give you an idea of what's happening during the different epochs. So let's start with the Paleocene. This is a picture of North America during the Paleocene. You can see sea levels were pretty high during this time. Notice there's no Hudson Bay. Okay, you should have the Hudson Bay right here. That's because the Hudson Bay didn't come until glaciation during the Pleistocene. Okay. Notice that during the Eocene, water levels were very high. Florida was totally submerged. You could see a lot of the lowlands here were submerged. Georgia, North Carolina, right? Where we're at in Texas was submerged. So this was all carbonate reef. And by the way, at this time, Florida was a very active limestone coral reef. Okay, so even this day, Florida is totally Florida has a very low average elevation. I think it's probably one of the lowest elevation states in our union, and it's also totally underlain by coral reef. Okay, old coral reef carbonate shelves. So that's why it's also very susceptible to sinkholes there in Florida. So next, during the Oligocene, temperatures were cooling down. You remember during the Mesozoic, things were very hot and very humid. So now in the Cenozoic, you're going to see this constant theme of things cooling, cooling, cooling. So during the Oligocene, things were starting to cool down, become drier. Much of North America was covered with savanna and grasslands. So this is a new kind. Now this is a really big deal. You're going to see this is a really big deal for Cenozoic life. We're going to start transitioning away from forests and rainforests and going to grasslands and savannas. And remember that grass is new on the scene, okay? Grass is an angiosperm. It is a newly evolved, it's the new kid in town, and it's going to be very successful at covering large swaths of the earth, especially as we transition to cooler, drier conditions, okay? A lot of moisture, a lot of heat, and kind of humidity is more conducive to forest land. But when you get drier and cooler, grasses tend to take over. So during the Miocene, Pliocene, temperatures are continuing to cool, and you start to get glaciation of Greenland, little glaciations forming, alpine glaciers forming in the highlands. And finally, during the Pleistocene, you get dramatic lowering of temperatures, and you get vast ice sheets covering all the way down into, you see Iowa, Illinois, Ohio, right? You had total glacial coverage of these states. Canada was almost totally covered with kilometers of ice, okay? Now, during this period of time, which lasted about 1.6 million years, during the Pleistocene, Earth went through 20 ice age cycles, going through glaciations to interglacial periods to glaciations to interglacial periods, switching 20 times during that period. So glaciers would recede and then rebound and recede and rebound and recede and rebound. And probably now that humans are on the scene and have kind of changed the climate and changed the Earth as much as they have, probably that's going to be the end of the ice ages. Maybe. Who knows? You know, nobody really knows what's going to happen. But it looks quite possible that we've put an end to these Pleistocene glaciation periods, but maybe not. So this period of glaciation carved out some of our dramatic landscapes that we have on Earth. Yosemite National Park was carved out by the glaciers of the Pleistocene. So now you can actually see exposed at the surface you can see the Sierra Nevada batholith. So, you know, this used to be buried 10 kilometers beneath the surface. So those glacial periods, glaciers are so effective at removing rock and eroding rock that, you know, eroded kilometers of sedimentary rocks off the surface here and exposed these batholiths at the surface. So pretty amazing. The beautiful fjords of Scandinavia, and also, by the way, might surprise you, there are fjords all over the place, not just in Scandinavia, but also in Argentina as well. Fjords of North America and Canada as well were carved out by Pleistocene glaciers. So there's beautiful inlets of the ocean to these U-shaped valleys. So these were places where glaciers were formed. These used to be filled with glacial ice, and the glaciers were, you know, moving down these valleys into the ocean. But now that the glaciers are gone, you just see this empty U-shaped deep-sided valley. So very beautiful. I just wanted to show you this picture because it's amazing. You might look at this and swear that this was a beautiful pavement built by somebody, but this is created 100% naturally. This is 100% naturally. Nobody made this. So what you're looking at here are columnar joints. Like, remember I showed you the Columbia River flood basalts? So these columnar joints, this at one time was a deep pool of basalt, but it cooled, and when it cooled, it formed those thermal, like polygon thermal cracks. Okay, it's just how as it cools down, it contracts, it forms these geometrical patterns, and then the basalt was eroded away by a glacier. And one thing that glaciers do is they polish the rocks that they erode, because they're abrading the rocks. They're using abrasion to polish these rocks, and so you get this beautiful flat polished look to the look. And you know, for all the world, you would swear this was built by somebody, but it wasn't. This is 100% natural. So this is what the world looks like basically now in the Holocene. So in the Holocene, temperatures rise due to the Milankovitch cycle. So this is an interglacial period. The vast ice sheets have receded, and they've left much of North America covered with glacial lakes. So you can see Hudson Bay has formed here. Okay, you can see the Great Lakes here, right? So there's Superior. I'm going to put S for Superior. There's Michigan. There's the Huron. There's Erie and Ontario. And you can see all of the thousands of lakes, Minnesota is the land of lakes, right? So because all these thousands of lakes have been left by the receding glacial ice sheets that used to cover Canada. So now conditions are relatively temperate and dry. They've warmed up compared to the Pleistocene. That has occurred naturally, but now there's this kind of we have made some impacts as human beings on the climate. So we don't know if we're going to go back to this. Maybe we will, maybe we won't. We'll see. In a way, I should hope that we don't. But we're kind of in new waters now because we don't exactly know what effect humans are going to have on the future of America's climate, but we'll see, or the world's climate. So we'll see. We'll see what comes. But just to kind of put your mind at rest a little bit, the Earth has been through it all, right? So it's been through high sea levels. It's been through warmer periods. It's been through times with a lot of carbon dioxide. So I'm not worried for the Earth. I don't know about people, but I'm not worried for the Earth. The Earth will survive. People will have to adapt, if we're going to survive. So anyway, just want to end with this last slide. And, it's kind of crazy, but here's all the major features that we have over the surface of North America. Okay, we have the Appalachian Mountains. We have the Gulf Coast Plains. We have the Ouachita Mountains. We have the Rocky Mountains. We have the Snake River Plain, the Columbia River Plateau with the Columbia River flood basalts. We have the Coast Ranges, the Cascades, the San Andreas Fault, the Great Valley, the Sierra Nevadas, the Colorado Plateau, blah, 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 the Canadian Shield up here. And I just want to point out that, wow, we've talked about almost all this stuff. Okay, I didn't talk about the Black Hills or the Kalmuth Mountains or the Coast Ranges. I guess I could have talked about them, but we talked about a lot of stuff. But now, you kind of got the full story of how America's geography came to be. So anyway, that's the end. And we'll talk next time about exciting Cenozoic megafauna, all the cool mammals of the Cenozoic. There's a lot of really cool creatures that have actually fairly recently gone extinct, But anyway, we'll talk about all that next time, and then we'll end up with humans, and that'll be the end of class. So, okay, I hope that you're getting ready for your final exam, because, your final exam is coming up, and it's good to start studying for that now, because it is a hard exam. It will challenge you, and it's hard, okay? It's hard. You saw what the midterm was like, and the final is only harder, so get ready. Start studying now. So with that, I'll end here. You have a good week.